all that stuff.
I was going to say, if the Department of Justice objects to posting it, well, you know, the government ignores the Department of Justice. Why can't we?
That's right. Not sure that's the best defense, but anyway. I said I'm not sure that's the best defense.
I wouldn't say
So, that and certain controlled substance. Yes.
Do you have any embedded videos inside your slide
I do.
deck? With audio?
Yeah.
Okay.
No audio, just video.
Just video.
Yeah.
Should be fine.
Yeah, I don't think we'll ever have any audio. Probably, as far as I don't think we ever have embedded audio in our videos, do we?
I don't recall any.
Yeah,
We got it covered. I just want.
Okay, no, nothing to it. Thank you. That was Eric, by the way.
Yes, right.
Yes.
Eric DeBob.
So I suppose we could ask him what we should do with the links, or should we just not ask? Maybe we just not ask for forgiveness later if we need to. That's what my watch says also. So.
We started the stream and there before watching. Were you able to share the link?
Great. Yes.
Great.
Yeah.
We're good. All right.
Great. Did we didn't send it out to the email list of undergrads, though, did we? I don't remember. Did I send them the website when I sent that email this morning? I said.
I don't know.
Yeah, you could. So when I sent out the email to the undergrads, I BCC'd all of them. Did I send a link to the website or anything? I don't remember what I sent. At that point, I didn't have the URL for the lectures, but I think it may be live.
Did you CC my Berkeley address in that email? Or was it through the CS267?
I think I CC'd your Berkeley address. Am I on or am I not on? Do you know? It looks like it's
No, it's
live.
red. Eric would tell us if it were.
Red light.
Button pushes sideways on the top.
Yeah. I'll go ask him. Okay. I'm confused about whether this is on or is it off, or do I need to just flip this switch?
It's currently on already.
Okay, so you've already been recording me.
Yeah.
Okay.
Picking up.
You want me to erase the whiteboard?
Sure. Might be confusing. We still have, there's a seat here. All right, I think we'll go ahead and get started. So welcome to CS267, Applications of Parallel Computing, also Engineering 233. I am Kathy Yellick, and I'm one of your three lecturers. You actually have three of us that are team teaching the course. I just want to start by saying that there is a live stream link to the lectures that we will be using, and so hopefully there's still seats in here. There's one here and a couple more on that side. You do have to all be seated in a seat, otherwise we have to stop the lecture and have you all leave according to the fire marshal rules. So there are about 130 people that want to get into the class, and we have, I think, seats for about 98 in this room. So, so far we're doing okay, which, and I think there's some people already watching it online. So welcome to those of you who are both in the room and online. So let me start by introducing those of us on the staff. So as I said, I'm Kathy Yellick. I'm both here in the faculty in EECS. I also have an appointment up at Lawrence Berkeley Lab and run the computing program there. I'll say a little bit more about that. Jim Demmel is also here. He's in addition to being a faculty member in EECS, he's the department chair for EECS, so that's why you've got three of us, because somehow between the three of us, we think we'll be able to cover the lectures. Unfortunately, Aiden had a little issue with his car, so he did not make it this morning, but he is watching online and will be here for some of the lectures, of course, later in the semester. And our GSI team, maybe just the three of you could stand up for a minute, and this is our GSI team, Ben and Aditya and Grace. They are all here in the front row. So, and by the way, at any point, if you have questions, just raise your hand and I will, if I'm not standing there in the spotlight, I will be happy to take them. Let's see, so I think that's, Jim's gonna take off and go to another meeting. Let me just tell you a little bit more about myself. Probably the other two lecturers will do this when they start. So as I said, in addition to being on the faculty here, I run the computing sciences program up at Lawrence Berkeley Lab. We will be using our supercomputers up there for the homework assignments. That's the NERSC supercomputing facility. And we also run the wide area network, by the way, for the DOE labs. So it's a Department of Energy. How many of you have been up to Lawrence Berkeley Lab? Okay, about a third. So we may try to have a field trip up there later in the semester, so you can go visit the computer room and see the supercomputers there. I also do research in computer science, and that's part of what I also run up at the lab is the research program. So that's me. What about all of you? So who's in this class? Well, about 60% of you are in some variation of electrical engineering and computer science. There's a seat over on this side, and we do need to have everybody seated. There's one more here in the front row too, so don't be shy. Come and sit in front. And the other 40% of you are spread out over all of these other departments. So welcome. It is the tradition in this class to try to encourage you to work in interdisciplinary teams. It is the way scientific software is built in the real world. And there's a lot of projects that have applied mathematicians, computer scientists, and domain experts from a particular scientific discipline. So we will do our best to try to teach this diverse group. What it means is for some of you, a particular lecture is going to seem pretty rudimentary, and for some of you it's going to seem maybe like it's going too fast, so please ask questions. We encourage questions from across the discipline, and I think that helps everybody in the class sort of to open the lines of the communication. One of the most difficult things, I've worked on a number of these interdisciplinary teams, is the communication problem, just trying to figure out how to talk to each other. I was in a meeting actually with one of my faculty colleagues on the campus. We were talking about a chemistry project, and we were in the meeting for probably about a half an hour to 45 minutes, and they kept talking about their systems and what they needed from their systems. And at some point I said, wait a minute, what do you mean by a system? And we realized that two of us were talking about computer systems and they were talking about chemical systems. So, you know, it takes a little while to sort of figure out what everybody means, even by terms that you think you know pretty well. So that's one of the things that you'll be hopefully experiencing as well in this class. In addition to those of you in the room, and I do need to have everybody seated, so there's one more seat in the middle there and there's one on this side. So please find a seat. There are students who are watching this class remotely. If you are an Exceed student watching it remotely, you should actually, the year is 2018, since this is going to be videotaped, you should be watching the 2016 lecture. So you're watching the wrong lecture if you're an Exceed student, and it's the spring of 2018. But these are all of the universities that are actually remotely taking this course. They're actually watching the 2016 lectures this year and some homework assignments that go with them. And we'll be developing some more of those kinds of homeworks and stuff for those. There are also, welcome to the NSF Mulsey Institute's students. They are hopefully watching remotely as well, and they will be watching these lectures and taking this version of the course. Okay. So what do all of you get out of the fact that there's these remote students? Well, we have 3 teaching assistants, which we probably wouldn't have if we didn't have some external support from NSF, and we also have auto graders and things like that that have been developed for the course. So what is this class about? Well, kind of historically, This class was about what we often call the third pillar of science, which is simulation, sometimes just called computation, which is maybe a little bit too broad a term. But it's really going back and looking at the scientific process. You know, back when you're in maybe middle school or grade school, you learn about science, and when you started learning about science, you learn about theory, you learn about experiments. You tend to start out with experimental science. You know, you roll cars down planes and you measure them and things like that. Maybe eventually you learn about F equals ma. So a really simple theory, and for much more complicated theories, we end up having to implement those theories as simulations and then often compare the results to experimental data. Now, what we're seeing now, is a fourth paradigm of science, which I guess is not showing up here, which is data analysis. The fourth paradigm of science really is looking at is going to look at data analysis from large-scale experiments on the next slide. So, what kinds of problems do we use simulation for? So simulation in science and engineering comes up for things that are, like say, too big, too small, too fast, too slow, too expensive, or too dangerous. So what would be some examples? Trying to understand the universe. Here's a picture of Saul Perlmutter with his, he is one of our Nobel laureates here, both at Lawrence Berkeley Lab and also on the campus. And he won his Nobel Prize for understanding the expansion of the universe, the accelerating expansion of the universe. And people today, and I'll say a little bit more about this, are simulating the universe in order to try to interpret that observational data. He actually used the computers at NERSC to analyze some of the data that he was looking at in these. He was looking at the observations, looking at supernova explosions that he used as standard candles, so kind of measurement points in the universe. We will actually have a guest lecture on this topic in cosmology later in the semester. Something that's too small, looking at proteins and diseases, looking at, for example, how proteins fold. Things that are moving too quickly, so you're trying to design a better more energy efficient jet engine. So this is looking at a turbulence process that happens and is something that can be very hard to see in a laboratory environment. Something that's too slow. Well, climate change may not feel like it's too slow, but the point is that you want to understand what's going to happen with climate change before it happens, and so running simulations is really the main way in which we've understood and been able to make predictions about what will happen with the climate. Okay, so there's my fourth paradigm of science, which is really about data analysis. And this is not something that used to be in this course, but over the last few years, we've really added a lot more data analysis. We'll have a lecture on machine learning and things like that, looking at large-scale parallel data analysis problems. So where do these big, huge data analysis problems come from? Well, once again, data sets that are too big, data sets that are too complicated. So scientific data sets are also often multidimensional. And in some cases have very high dimension that you're trying to reduce. The data can be streaming. It turns out that these kinds of devices, so telescopes and particle detectors and so on, are producing data at very rapid rates. So you have to do on-the-fly data analysis of some kind. The data can be very noisy. Here's one of my favorites, which is a carbon sensor. So one of the lab scientists that works with carbon sensor data, Deb Agarwal, who's up at the lab, they run one of the community or manage one of the community data sensors for these kind of carbon sensor data. She said, well, one of the problems they have is they've got to clean the data. So what does that mean? Well, birds come along and they drop things on the sensors, and that causes a spike in the sensor data. So they literally go through and take the data and they clean out those spikes to make the data look uniform, which is a great thing. Although if you're familiar with one of the cosmology problems I talked about earlier, cosmic microwave background, that's a blueprint of what we saw in the Big Bang, and that was actually something that originally looked like spikes from pigeon droppings on these radio telescope sensor detectors. So you have to be really careful when you throw away some of this kind of data. But the point is that in many cases, these data sets are large enough that we also need parallel computers in order to analyze the data. Let's see, so we've got one more person standing. Are there any more seats? Does anybody have an empty seat next to them? Oh, okay. I think one of our TAs is going to vacate the room and go watch on the live stream so you can sit down here. Okay. Got to prioritize these things, so thank you, Adi. All right, so let's see. Why do we need really big computers? I'll say a little bit more about this in a minute, but here's one example, and let me see if I can get my movie to work here. This is some climate modeling data. And this is actually looking at hurricane season, and you can see these big swirls forming there in the Pacific, also some other ones over here in the Atlantic hitting down there by Florida. So that's it's looking at the effects of climate change on the number and the intensity, the amount of moisture and things like that are in the hurricanes. So what happens, why do we need faster computers for that? Well, this just gives you an example by looking back in time at what these simulations look like if you were running at a much slower computer, so a computer about 10 years old. You would see something that looks like the top. So this is the same simulation I showed on the previous screen. This is a simulation that would have been run on a computer, say, about 10 years ago. That has a 200 kilometer resolution. This is a 25 kilometer resolution. So this is still pretty coarse, right? This is still, it means between, what this means is the amount of data that's in the simulation, even down here in the detailed simulation, is one set of variables every 25 kilometers on a mesh spread out over the globe. And that is fine enough that you can see things like hurricanes forming, but it is not fine enough, by the way, to see cumulus clouds, which are really important in understanding precipitation. So one of the reasons that people want even faster computers is so that you can do simulations that resolve the clouds, that actually have a real mathematical model of what clouds look like. Okay, so we got one more student in the back of the room, maybe. I think maybe both Ben and, okay, Grace is gonna leave. We'll have you come and sit down here because we can't have people standing. I'll just say this one more time. We are trying to admit everybody in the class who wants to get into the class. What that means is you may not all be able to come to lecture, but they will be webcast, and they are being webcast today. So anyway, that's why we're gonna let a few more people in than actually fit in the room, is just so that everybody who wants to can take the class. Okay, so that's just to give you a little bit of an overview. Any questions about kind of broad scope? I know I haven't really said anything very technical yet, but. Okay, so I'm going to talk next about some of the fastest computers in the world. This is just to give you a little bit of context for what these kinds of high-performance computers, parallel computers, are about. And then we'll talk about a little bit about some of the science needs in high-performance computing, and that include both simulation and data analysis. We'll look at why these high-performance machines are parallel machines, but also actually why all machines are parallel machines these days. And then we'll talk about a little bit about performance programming, how to measure performance, some basics on how you measure and report it, and then we'll look a little bit more at some of the other things that we'll learn in the course over the semester. So I'm going to start with the top 500 list. So these are some of the fastest computers in the world. They are the computers that are actually reported in the top 500 list, so it's not necessarily every supercomputer in the world, but there are these computers that are used especially for scientific calculations are often, they run a benchmark on it called the High Performance LINPACK benchmark, and they use that to then make a list of the fastest 500 computers. Now I actually think this is a really interesting list for historical reasons. So Ben, we have our last student who's come in. We're going to lose all of our GSIs, which is maybe not the best. You have to sit over here. And after this, we're going to send students out to go watch on the live video stream. So, okay, thanks very much. Okay, so what are the measures of these fastest computers in the world? So there's great amount of historical data. So we no longer have room in the room, but you can watch it on a live stream. And I encourage you to do that. Look at my webpage, and there's a link to the lecture notes, and that has a link to the live stream. Okay. I guess we could have left the GSIs in here because we're going to end up throwing students out anyway. Okay, so first of all, a little terminology. So when we talk about fast computers and big computers, we talk about how many floating point operations they do per second. So we call those a flop. It's a little confusing because we're usually talking about floating point operations per second, which I try to write as flops per with a little /s, so flops per second, although not everybody is that consistent, so sometimes you'll just see flops with without the slash in it, and that means it still means floating point operations per second. We of course also care about the size of the data set since we're looking at data analysis problems, and of course that'll be in bytes. So you're used to seeing these kinds of numbers like kilo, mega, and giga for things like buying memory in your laptops and things like that, or looking at the performance, the floating point performance, or the number of operations per second, integer operations or floating point operations that your computer can do, probably. You may not be so familiar with tera, peta, exa. And exa is, by the way, we're right here. We've got petascale machines. So the machines that you'll be using in this class, the fastest one is about a 30 petaflop peak machine. I'll say more about that in a couple of slides. The Department of Energy is trying to today build an exascale computer, and there are actually a number of other countries that are trying to build exascale computers. So Japan, the European Union as a group, and China are all working on exascale computers. So exa, after exa, to my surprise, comes zeta, and then after zeta comes yada. So it's a little bit non-alphabetical there at the end. But anyway, those are the kind of big sizes of big computers that we tend to talk about. And as I said, the data that I'm going to show you, most of it is available on the top 500 list. There's actually a searchable database. And I think to me the most useful thing about the top 500 list is that it gives you some historical perspective on how these supercomputers or high performance computers have changed over the decades. Okay, so what is this? It solves, the benchmark that's used in the top 500 list is called the LINPACK benchmark, or actually often called the High Performance LINPACK benchmark, or HPL. There's a standard implementation of it that people can take and can adapt to their machines, although you can also write your own version, although there's certain rules about you have to solve it in a particular way. You're solving AX equals B, where A is a large dense matrix that is dominated by dense matrix multiplication. If that is not obvious to you, we will talk later in the semester about dense linear algebra and these dense linear algebra algorithms and how solving a dense linear system gets turned into matrix multiply. In the next lecture, I'll actually talk about dense matrix multiplication, how you optimize that on a single node. But it's one of the things you should know about it is very computationally intensive. It is an order n cubed operation, set of operations on order n squared data. So there's a lot of floating point operations per memory operation if you organize the computation correctly. So that's one of the reasons I think it was chosen as the benchmark. It was also chosen as the benchmark because I think, in 1993 when this started, a lot more scientific computing was done with dense linear algebra. There are a lot more sparse matrix methods that are used today, and you'll hear about how you parallelize those kind of methods in this class. But as I said, this kind of benchmark, the dense linear algebra, still gives you a nice benchmark of how fast the machines are. A lot of debate about whether it's a good benchmark or not a good benchmark because it doesn't necessarily reflect what people do on the machines in scientific simulations. And in fact, one of the things that's been surprising to me over the last couple of years is a particular workload dominated by dense matrix multiplication that is very important and is, can somebody tell me what big computations that people do are dominated by dense matrix multiply? Surely somebody in here knows. How data analysis problem comes up in machine learning, yeah, deep learning algorithms, right? So deep learning algorithms, one of the things they've realized over the last few years is that you can run them on, you can organize it as dense matrix multiplication, and therefore it runs on some of these very fast supercomputers actually very well. So in some sense, kind of ironically, these data analysis problems maybe now are a better fit to the LINPACK benchmark than most of the simulation problems that we do. But anyway, and we'll see, maybe that will change also over the next couple of decades. So this list is published every twice a year, once in June in a conference, ISC conference in Germany, and once at the SC conference, which happens in November of every year. Okay, so it's all on this website. So here's what the top 10 systems on the list look like. And the yellow ones are systems that are either new to the list, or like in the case of the Trinity system at Los Alamos, it moved up on the list because they installed a bunch of new hardware in the system. The others were on, the white ones were all on the previous version of the list, and usually what happens is you slide down the list. So you start up near the top of the list, and over some number of years you kind of fall down further and further until the system gets repaired. It gets retired. So What is the two fastest supercomputers in the world are both in China, the Sunway Taihu Light system and the Tahane 2 system. And I'll say a little bit more about the Taihu Light system in a minute. And then let's see, Titan is the fastest system at this point according to the benchmark in the US. That's a system at Oak Ridge National Labs, one of the other DOE labs, and Lawrence Livermore National Lab, not to be confused with Lawrence Berkeley National Lab, also has one of the fastest computers in the world, Los Alamos. So there's DOE lab, DOE lab, DOE lab, DOE lab, all in the US. This one is the system that you will be using in this class. That is the NERSC Cori system. So not too shabby. It came in, I think, originally at number 5. This list is now, about a year ago, it is now at number 8. So there's a lot of movement usually in these top systems. So let me tell you, though, a little bit about the system in China. I was actually in China last summer and got to visit the system in Wuxi, the center in Wuxi, China. And so this is the Sunway Taihu Light system. It's not the greatest picture, I guess. I didn't realize how pixelated it is. It is a 125 petaflop system. And the LINPACK number, and this is actually quite impressive, is 105 petaflops. So the peak number, and you'll hear this a lot, we'll talk about peak performance of the hardware, is the guaranteed not to exceed number on the hardware. That is the number of floating point operations that in principle the hardware could do. In practice, you have to get memory to them and things like that. So a lot of times this LINPACK number will be substantially lower. That's a pretty good number at 105 petaflops and is what puts it at the top of the list. It's a 15 megawatt computer. So for those of you who don't pay power bills on supercomputers or other really large devices, I can tell you as somebody who does that up at the lab, that's about $15 million a year of electricity. Okay, so just order of magnitude. We get our power at the lab. It's a little bit cheaper than that, but just to give you an order of magnitude, your power bill is $15 million a year. The cost, and I put the cost here because it's on Wikipedia, so who knows? I have no idea who put it there or whether this is right, but what they estimated is a $273 million supercomputer. So very big, very expensive supercomputer. The processor is a custom processor they designed called Sunway, or is a Sunway line of processors. They're actually working on a new version of that for their exascale computer. It has 256 cores on a single chip, so a lot of processor cores. For those of you maybe outside of computer science, hopefully you're familiar with the different terminology. This was something the marketing people, I blame them for this, but years ago when we started sticking multiple cores on a chip because we couldn't make single processors any faster, they decided that it didn't sound good to say there were multiple processors on a chip, so now we have processors that have cores on them, but that's still a lot of cores. So in your laptop you probably have 2 or maybe 4 cores on your chip. Your graphics processor may have a lot more than that, but still that's a lot of cores for a general purpose processor. Clock speed, not so high, 1.45 gigahertz, but that's because you're trying to keep the power down. The whole name of the game to build these kind of computers is you're trying to get as much compute density into a fairly small region that you can, so that you can, this machine room, by the way, is well, probably at least maybe 3 times the size of this room. So, you've got to get data across that machine. You don't want it to be 10 times the size of this machine room, or you'll be really limited by the speed of light getting data around in it, and probably more importantly, the cost of the cables in the system. So you're trying to make things very dense, and you can't do that if you make the clocks very hot, and we'll talk more about that in a little while. So it's got a bunch of memory and storage associated with it. Now in this class, as I mentioned, we'll be using this system called Cori, and also, I think I didn't highlight it here, there's the Cori system, and then another system called Edison, which is an older system at NERSC. NERSC uses both, has 2 systems at a time that it runs in the steady state, and so this is the system that we've used in the previous versions of the class, and you'll probably, in some cases, you may have a choice of which one to use, but we're trying to move all the homeworks over to Cori. So what does Cori look like? Well, it actually came in 2 pieces, which is a little bit confusing. There's the phase 1 piece, which, by the way, looks a lot like Edison, and it looks a lot like kind of a standard computer cluster other than the network. It has a Haswell processor in it, a pretty fast processor, just 16 cores per chip, so a lot smaller than the 256 that you have on the Taihu Light system. And it's the peak performance on this system is only 2.8 petaflops. I don't think it might even not be in the top 500 at this point. I don't remember if they ran the benchmark on it. Sometimes people just don't run the benchmark because it takes a long time to run the benchmark, by the way. Then there's a second phase of it that is connected together in the network, but is kind of run as a separate system in terms of submitting jobs into it. You can run them either on phase 1 or on phase 2. That's a 28 petaflop system in terms of its peak performance. You can see that its LINPACK number not so close, right? So the other system was 125 petaflops versus 105 for the LINPACK number. This one is about 50% efficiency in terms of 50% of peak performance on the LINPACK benchmark. And actually in about, I think, a week and a half, one of the experts on trying to get performance out of this architecture, Sam Williams, will come and give a lecture about this architecture and his performance tool called the roofline model, and tell you more about kind of why we see that kind of a gap. So a lot less power, only $4 million a year in the electricity bill. But what does it have in it? It has Knights Landing processors. So it doesn't have 256 cores per processor, but it does have 68. So it still has a fairly large number of cores on it relative, once again, to what's in, say, your laptop or other server. Yes?
What was the cost of this, if you happen to know?
I happen to know, but I actually can't say that. So that's why I didn't put the cost on this one. So I know it a little bit too well. So yeah, but it's a lot less than the Chinese machine. I'll put it that way. Yeah. Yeah, so, but a good question. Any other questions? Okay, so let's see. So this top 500 list, it has 500 machines on it. I only showed you the list of the top 10 because they're some of the most interesting machines in terms of their architectures, and there's a lot of effort that goes into trying to figure out how to build a machine that has that kind of performance. But this is looking at the history starting from 1993 up until 2017 of the top 500 list. N1, that is the fastest machine on the list. So what happens, as you can see this in the pattern of that red line there, is that some big machine will come in. So actually the Japanese Earth simulator was back here. It was sort of on the top for a while, and so you'll see a pretty level line for a little while. There's the Taihu Light up there, and I think the string of before that might have been a previous Chinese system, actually. So I think it was the Tahane system. So that's kind of a bumpier looking curve. The other interesting thing is, what's the slowest machine on the list? So what does it take to even get onto the list of the top 500? Today you have to be over a half a petaflop in order to get a machine on the top 500 list. That's half a petaflop of LINPACK performance. And what is the total sum of all of the machines on the top 500 list? This can also be really interesting to just look at kind of what do all the machines look like. And there's a lot of analysis, for example, on the machines. I'll give you just one of them, but you can also look at what countries they're in and various other things about the architecture and so on. One of the things that people have looked at is the age of the system. What is the average age in months of the system on the list? And so what you can see from this curve is that historically things have been retired off the list much more quickly than they are today. And that is for all the reasons that we're going to talk about a little bit later about processors. It's harder and harder to get faster processors. It's harder and harder to get faster supercomputers. So things stay on the list longer than they used to. So that's just sort of one characteristic that we'll see when we talk about some of the challenges of getting more performance out of computers. So here's one of the other kind of analyses of the systems that are on the list. Again, this is from 93 up until today, and they're roughly categorized into these different groups. So at the beginning, when they first started reporting these numbers in 93, there were a bunch of vector supercomputers still around. These are these Cray supercomputers at the time, vector supercomputers. They were really single processor machines that had large vectors, and it turned out that those could be programmed by just annotating some serial code. So we might not have to teach this class if that's the way the supercomputers looked. You would take, at the time, Fortran code. By the way, Fortran is still a pretty popular language in a lot of scientific code. But you would take your Fortran code and you would annotate the loops, and those would parallelize pretty well, vectorize, that is, over these big long vector lanes. And then we got into the stage where it turned out that you could build massively parallel machines that were much faster than the kind of vector supercomputers, and so these MPPs, or massively parallel machines, came into play, and they're still around today. There's a lot on the list right now. Actually, the dominant set of machines are what are called generic clusters. They look a lot like the MPPs. The difference is these blue ones tend to have custom networks in them made by companies like Cray or HP or whatever, whereas or IBM, and the MPPs, sorry, the ones that are called clusters will have either Ethernet. Typically, though, they'll have an InfiniBand network because it's a little hard to run a benchmark like the LINPACK benchmark if you don't have a fast enough network. Although it's pretty computationally intensive, you still need a decent network in it. So that's what the machines look like today. The other thing we've seen recently is a lot more introduction of some kind of special purpose or specialized accelerator. So today, these typically are GPUs. So the orange piece up there that's come into the kind of market in high performance computing are graphics processing units. And there's been other sorts of things. The Xeon Phi which is the Knights Landing that's in Cori, isn't technically an accelerator because it's it just is self-hosted. It lives by itself. But we are seeing more of these kinds of things attached onto the processors. So this also means that you have to think a lot harder about the parallelism, right? So as soon as you get to a network connected of different kinds of processors, you have to really think about how are you going to take your data structure and to spread it out over the processors, and what kind of a parallel algorithm are you going to use to coordinate that computation over the processors. And you also have to think even harder then if you have, say, graphics processing units inside of that network of processors. So now you have multiple problems. You have to worry about how you're going to program the GPUs, how are you going to program the CPUs, how are you going to program the between the network and the coordination across the processors. So things have definitely gotten harder. Just one last slide from the top 500 list. This is the kind of accelerators that you see in the top 500 list over the last, whatever it is, 10 years or so. This is, you can see there were, there's NVIDIA had a big set of the Fermi processors. Now we've got some of their more recent ones. So the NVIDIA processors are pretty dominant. The Intel Xeon Phi which actually is a main processor, not just an accelerator, is also common. As I said, that's in the Cori system, and it's in some other systems like the one in Switzerland and others. So any other questions about kind of these supercomputers, or kind of, the history of the fastest machines in the world? Okay. So let's switch, and we're going to talk a little bit about science now. And I'm just going to give you a few examples of science problems that why do people build these supercomputers? And they build them in order to solve science problems that you can't solve on a smaller computer technically. And as I said, today the computers are petascale systems. What I'm going to talk about are some examples that are mostly part of the DOE exascale computing project, which means they're applications under development to run on the exascale computers. The projection is right now the first exascale system, or the plan, DOE's plan is to have the first exascale system in 2021. I think China has announced that they'll have their first exascale system in 2020. I think it was originally 2019. These things have gotten harder to build, but that's kind of the time frame. So it's not that far in the future. And so what DOE is doing, which I think is really great, is developing a bunch of applications that will solve new science problems using these exascale computers in parallel with the systems being developed, so that once the systems are available, you'll actually have interesting science that can be done with them. So as I said, mostly these big high-performance computers historically have been used for simulations. They've been used for simulating things like cosmology, so the entire universe, astrophysics, what happens when a star explodes, accelerator modeling. That's a project up at the lab looking at how do you design the next generation of accelerators that are used for advanced instruments for science and for light sources for looking at little tiny things, so on. even for medical applications. There's problems looking at simulating the devices that you put in a coal burning plant to try to capture the carbon that's being so that it doesn't get emitted into the atmosphere, that you trap it and then do something else, such as put it into the subsurface. So there's a second piece of it, which is sequestration, but that's one of their big simulations. Chemistry and materials, these are actually, the two taken together are the dominant workload at NERSC. I would say about let's see, a third to even close to, I think about a third of all the work that's done, the computing that's done at NERSC, is either a chemistry or materials simulation problem. So looking at designing new materials for batteries, things like that, done with computation. And looking at, I'll say a little bit more about the subsurface. There's also an earthquake simulation looking at how do you design buildings that are really designed for the particular environment. So current codes are basically generic. They say you need to build a building that has this kind of characteristic. These simulations are designed to get information about what the land underneath, say, the buildings look like, and then try to do simulations that will tell you exactly what kind of a building structure needs to be designed in that type of environment. So there's other problems here that I've put on the data analysis side, and there's a big project in using deep learning for cancer genomics. There's another, I'll say a little bit more about these other two. There's some that are not technically part of the exascale, the DOE exascale project, but looking at very large analysis of brain images and looking at transportation. So say the ITS institute here on campus, the Institute for Transportation Studies, is looking at very large-scale optimization algorithms to analyze transportation data and then figure out how to design the transportation network. So, so what are the kind of generic things that make you want a faster computer when you're solving these science problems? Well, on the simulation side, it's you want higher resolution. That's the most obvious, okay? We've got our climate model. It only has data stored every 100 kilometers. We want it to be 10 kilometers, or we're down to 10 kilometers, and we want it to be 1 kilometer so that we can actually resolve clouds. And that happens a lot in a number of different application domains. Second is multi-physics. What that means is I've got a simulation of, say, some kind of a device that has maybe combustion in it, such as an engine, but now I want the mechanics of it. I want to know things about, or what happens with the chemical reactions in that process. So I want to combine together fluid dynamics with chemistry or other kinds of physical phenomena. Multi-scale means that I want to work across the different time and space scales and take algorithms that will actually simulate at these different scales and put them together in a way that gives you meaningful results. On the data side, the size of the data set is kind of the most obvious thing that drives the size of the computer that you need. But sometimes it's just the complexity of the data and the amount of computation required to analyze that data. And the multimodality then has to do with taking data from different types of sources. So for example, in the brain case, you might have fMRI data, you might have some other kinds of imaging data. You want to put all of this together, or in other biology applications, genomic data combined with imaging data, and put these different data sources together. But the main point I want to make is actually that these are not two different kind of independent parts of doing science. And in fact, when we talk to scientists across the lab at what they're doing with what are their large computational challenges and what are their large science challenges in general, in many cases what you see is that people want to take simulations and combine them with data analysis. They want to take machine learning and use that to improve their simulations, or they want to take simulations and use that to help interpret the data that they're seeing from observations. So let me make this more concrete with just a few examples. So the first one is a subsurface simulation. This is led by Carl Stiefel up at the lab. And this is some former simulations that were done at the petascale level, looking at what you're trying to figure out is what happens in porous structures underneath in the subsurface, underneath the Earth's surface. And you might want to understand that because you're trying to do carbon sequestration. So you've run some carbon capture, you've gotten a bunch of carbon, you're now trying to figure out where can you store it. Or you're trying to figure out what will happen if you do drilling, or if you do, in particular, fracking, which is going to perhaps create extra fractures underneath in the subsurface. And the question that they're looking at for the exascale era is what will happen in one of these fields where you have bored a bunch of wells in the field after 100 years. So you're trying to understand, if you're doing, say, fracking, what will happen 100 years from now with the stability of that field. And it has to do with these kind of fluid dynamics, but it also has to do with these structures, these very fine structures, and what does the porous makeup look like. In climate science, actually a couple of projects at the lab. One of them is looking at ice sheet modeling. So this is actually some recent simulations from about a year ago looking at what would happen if the ice sheets in the West Antarctic ice sheet were to melt, and what will it do to sea level rise, right? So there's a very specific question having to do with the impact on sea level from doing these simulations. It turns out that climate, I'd actually put it on the data analysis side, which most people would say it's a simulation problem, but it is something that fits in between, because you're also trying to look for extreme climate events or extreme weather events inside of your climate simulation data. So if you're running, as they often do, a 100-year simulation of a climate model, and the question is, are there more hurricanes if I have, if the temperature is 2 degrees warmer than there would be if it's 2 degrees cooler? And so what you want to do is count all the hurricanes across a 100-year period. And while a hurricane may seem like an extreme event that you can't miss, you don't necessarily want to sit there and try to identify these by looking at visualizations of the simulations. You want to count them in a much more rigorous and quantitative way. They're also using machine learning now to automatically identify certain kinds of patterns in weather events of various kinds. So one of the cool science results is in astrophysics. This is led by Dan Kaysen, who's both here on the campus and also at the lab. I should have said the climate one is, at least part of that work is led by Bill Collins, also here on the campus and at the lab. This is looking at astrophysics. So a lot of news recently about this discovery of gravitational waves coming out of a neutron-star merger. And interestingly, Dan, who's been doing these kinds of computations for a long time, had actually predicted the light patterns that they were going to see from a neutron-star merger before the observations happened. So he was, I think he said, quite nervous, but also very excited when the observational results came through from LIGO and Virgo that confirmed what he had been predicting in simulations. Now his simulations, why do they want an exascale computer? One of the reasons is to identify where the heaviest elements come from in the university, because from these kinds of astrophysics events you get these heavy these heavy elements that are produced. And I think in the simulations, which you can't, at least, or haven't been able to predict so far or confirm from observations, is that this type of a neutron star merger that was observed would produce about 200 Earth's masses of gold and about 500 Earth's masses of platinum. So a lot of heavy metals coming out of that. So one of the things that as I said, that drives the need for more computing is the data collection that we're doing in various scientific instruments. This was a graph I put together, which is very notional, so you shouldn't look at this as very kind of hard data, but I looked at the exponential growth rates on 4 different things. One is the speed of detectors. So those are the say, CCD devices and other related devices that are going inside of telescopes. They're going inside of the light sources, such as the Advanced Light Source, which is up at Lawrence Berkeley Lab, or the one that's at SLAC. And they're going inside of particle detectors, say at the Large Hadron Collider in CERN. So these devices are getting denser, and the rate at which data is coming out of them, the rate at which they can collect data is growing faster. And so they're actually on a super Moore's Law curve that is growing. These were all just sort of started at 1 and looking at their exponential growth rates. So they're enjoying still an exponential that's much higher than the traditional Moore's Law curve there, which was processors. Actually, I think that is actual Moore's Law, which is transistor density. Genome sequencers, and if you're familiar at all with genomics, or if you read about the cost at which we can collect for collecting the data, and this has to do partly with the speed at which you collect data, but this curve is really about cost, that is also growing at a rate faster than processing speed. Now, you may say for data-intensive problems, we don't really care about processing speed. What we care about is memory speed, and that's, of course, even slower than the improvements in processing speed. So the point is that in many of these scientific disciplines that are looking at data from genomics, looking at data from embedded sensors out in the environment, and I haven't even talked about sort of the ubiquity of these sort of sensor devices, which is also increasing the size and availability of these data sets, where you're looking at particle data from the LHC or whatever. You're seeing data sets that you used to be able to analyze, say, with your MATLAB script or in your on your home, on your laptop, and now requires a much more sophisticated device. And in some cases, for example, in the Large Hadron Collider in CERN, the data rates are so high that they can't actually get the data off of the detectors. So you actually have to put algorithms in the detectors to collect the data before it gets exported, so off the detector device, and so you're only getting a subset of the data off of those devices. And we're seeing that happening in other domains as well, where you've got, say, a genome sequencer, and you're trying to figure out what is the kind of minimum amount of information I need to record that's coming from this sequencer, rather than producing kind of all the raw data, because it's too large to even move it off the detectors some other place. So just a couple of examples of this from the Exascale project. One of them is in photon science. So up at the lab, we run something called the Advanced Light Source. It has got these photon beams, so you can look at lasers and things, and look at really small materials, proteins, and look at their structure. And you can also, in some cases, look at their dynamics, or at least that's one of the most challenging problems, is can you look at a protein, for example, as it's folding. So what's the problem here? Well, you've got these great detectors that can collect all of this information. You get an image that comes out of it, but you had to figure out how to put those images together, because you're taking multiple pictures, and the question of how the data all fits together is a mathematical problem. In order to get back to not just a two-dimensional structure, but actually a three-dimensional structure of what you're trying to see. And so that's one of the challenges that they're working on as part of the Exascale project. And the last one is actually a project that I'm leading along with Aydin Bulic and others, looking at genomic data, but it's not looking at the human genome, which is, I think, the thing you typically hear about. It's looking at genomic data that comes from the environment. And so what's the difference between environmental data and human genome data? Well, there's a couple of them. One is that when you scoop up, say, some bit of this microbial mat that's sitting in Yellowstone, what you see is not a single genome that you can sequence, but a whole bunch of genomes all mixed together. So you've got a whole bunch of microbial species. Furthermore, there's no reference. So in the human genome, because of the Human Genome Project, there is a reference of what kind of a standard human genome looks like. And even though all of us are a little bit different, you can take that standard reference genome and you can use it. It's like having the cover of a puzzle, and you know what the picture is supposed to roughly look like, and you can take a piece, because what the sequencers do is they spit out the genome in little fragments. They don't spit out the whole, let's say, chromosome at once. So you can take those pieces and you can say it goes right about here in this puzzle, and you can use that to put the pieces together. In the case where you're looking at microbes, these microbial species, you have the problem that you've never seen them before in many cases. So you don't have any reference for what they all look like. Some of them you may have in a database a reference to, but in many cases you've never seen them before. Secondly is the problem that you don't just have one species together. So now think of it as putting together a puzzle, because you've got these little fragments, but you've taken, say, 100 or even 1,000 different species and dumped all the puzzle pieces together, and you have to now assemble them. You have to put them back together in pieces. That's a large-scale computational challenge, especially for environmental data, which tends to be even more complex than say, data that comes from, say, the human gut microbiome, which we also know is very important to health and is also one of these mixtures of microbial species. Jill Banfield, who's here on the campus, also at the lab, has used this kind of analysis of these microbial data sets to to identify new CRISPR systems. In this case, it was found in a underground crystal geyser, looking at the bacteria in the geyser. So I'm sure you've heard of CRISPR. This is looking at, so there's many applications of these kind of microbial species. Some of them are health related, but many of them are also environmentally related. So that's why the Department of Energy and Berkeley Lab really are interested in that kind of biology, is because you're looking at how do you use these microbes to, say, produce something that you care about in biomanufacturing, or use them to understand what will happen if the climate warms by 2 degrees. There again, a question would be what kind of microbial species will survive, what kinds will grow, and will they release carbon or absorb carbon? So those kinds of questions have a lot of impact on the environment. So mostly I've talked about basic science, and that's kind of my experience from working at the lab and working with a lot of scientists across the lab and across the DOE lab complex on various scientific applications. But there are economic drivers for high-performance parallel computing as well. So the airline industry looks at things like optimization systems that they use parallel computing for. They estimate that by doing this on these large-scale computations, they save about $100 million per airline per year. Automotive design, another big area of engineering for high performance and parallel computing. This is looking at CAD/CAM systems for things like crash simulations and aerodynamic design. And some of these have actually, that data is probably a little bit old, but some of them have very large scale parallel systems. I think one that's not on here is the pharmaceutical industry. The pharmaceutical industry also looks a lot at this genomic data analysis. They have supercomputers as well. You tend to not hear about these quite as much, and you don't see them on the top 500 list because they consider it a competitive advantage. So, companies that design tires, company that designs semiconductors, they use large-scale computing as well to design the devices, maybe to understand also the materials that you're using in the devices. So at different scales, they're using large-scale simulations. And then the energy industry is also looking at using parallel computers for things like modeling of nuclear power plants and so on. Okay, so that's at the end of my science overview. In the next few lectures, we'll go into a lot more detail on what's underneath these parallel computing problems and the systems. But are there any questions about any of the science examples? Anything else? Okay. So why are the fastest computers parallel computers? In fact, it's not just the fastest ones. Why are all computers basically since 2005 parallel computers? So now we're going to go down into kind of the underlying drivers of computer science, engineering, electrical engineering, and a little bit about what the motivation for going with parallelism. We'll start with some funny quotes from the experts in the field about computing. The first one is from Thomas Watson, who was of course, chairman of IBM. He says, I think there's a world market for maybe 5 computers. Okay, so the second one was, there's no reason for any individual to have a computer in their home. That's from Ken Olsen, who was the president and founder of DEC. Bill Gates, 64K of memory ought to be enough for anybody. Of course, he then went out to make sure that it was not enough for anybody by making sure we had software that would not possibly fit in a 640K of memory. And the last one is actually from Ken Kennedy, a colleague in parallel computing, actually like myself, where he worked on compilers and programming languages for parallel computing. And his quote, which was from 1994, is, on several occasions I've been asked whether parallel computing will soon be relegated to the trash heap reserved for promising technologies that will never quite make it. And that was kind of the view in 1994, that there were a few crazy people like me and Ken and others and Jim working on parallel computing, but most people said this stuff is never going to go anywhere, and there's only just this kind of esoteric fringe of people that want to do these huge science problems or want to build these big supercomputers and get their computer on the top 500 list. They're going to build these parallel computers because they're way too hard to program, right? And that was absolutely the view, is that they're way too hard to program, and so people didn't want to use them. Okay, but what happened? Well, part of the reason why that was the prevailing vision at the time was because Moore's law was very successful, not only at producing smaller, denser transistors, but also then getting some performance that went with them. So here was the Moore's law that said transistor density is really not about computing performance, it's about transistor density doubles every 1.5 years. Therefore, microprocessors became smaller and denser and more powerful. By the way, economics of this is also really important. They became cheaper, right? The amount of computing you could buy for $1 was improving exponentially. And in fact, I think that Moore's law has been in effect for so long that it's kind of ingrained in our minds, even as computer scientists who realize that, for those of us in the audience and for myself, who realize that there's this problem with Moore's law going forward, but it's so ingrained that we just expect that we could just design a parallel algorithm that's going to, or any kind of an algorithm that's going to take a huge amount of computing time. And if it's not practical today, such as convolutional neural nets, maybe in 10 years it will be practical because computers always get faster, right? But this, and part of this is due to the fact that transistor density was improving. Okay, and so that was, of course, from Gordon Moore. So this was, at the time, this only goes up to the year 2000, was looking at transistor density, the blue line, and it wasn't quite keeping up, but there is the clock frequency, so the rate at which processors could execute instructions was going up at least kind of comparable. I mean, there's a growing gap there, but you could see the rate at which processors were running was growing up. And so in the mid-90s, and even up until about the mid-2000s, people just assumed that this was going to go on forever. Transistors would get denser, and frequencies would get faster. And there were some people saying, no, this is not going to go on forever, but mostly people told them to be quiet. Okay, so why is it that having smaller transistors gives you a faster processor? Well, what happens when you shrink the feature size, that is the transistor size, by a factor of x? And this is a gross oversimplification, but just bear with me. So what happens is the clock rate goes up by about a factor of x because all the wires become shorter by a factor of x. Okay, so that's the first thing. The transistors per unit area, because that's now in a two-dimensional surface, goes up by a factor of x squared. The die size has actually also kind of coincidentally with this was also going up by almost a factor of kind of comparable to Moore's law. So we'll say that's another factor of x. And therefore the computing power, the number of transistors on the chip and the speed with which those could operate was going up by a factor of x to the fourth. And now not all of that was actually used for just making faster clock speeds. So even back when Moore's law and the processors were getting faster, a lot of what was happening is we were actually already putting parallelism into our processing chips, and we were putting more memory on the chips, because the problem is you got this processor that's getting faster and faster, and this will be a recurring theme throughout the semester in this class. You can't feed those processors, you got to get data to them, and that's the limiting factor. So you're sticking some amount of memory on the chip called caches. So But a lot of programs are running on the order of x cubed times faster without doing anything to the programs, right? All this parallelism, it was hidden inside of the microarchitecture. You didn't see it. Now we see it because we hear about it in things like security violations, right? Because processors are running ahead and doing things in parallel, and we weren't paying attention to it, and they are reading memory they're not supposed to read and things like that. But that's what is, most of this was kind of happening. It was kind of a free ride for the software people. The hardware people were making the processors go faster, and we weren't doing anything about it. So and it didn't need to do anything about it. So what happened? Well, also oversimplifying, I know some of you are much more expert on this, but just for the people from outside, just to kind of get a sense of what happened, is we ran into power density limits. Okay, so this is a nice graph from I think Shekhar Bokar at Intel, although he attributes it to Patrick Gelsinger. And, well, actually from both of them, I guess, at Intel. So this is looking at the power density, that is the watts per centimeter squared of various processors. So there's our Pentium processors, there's the P6, and so on. And that trend line that they were on, you can see was going to hit, the heat density of a nuclear reactor, or the heat density of a rocket nozzle, or the sun's surface. Okay, so now you've got a laptop, and by the way, my laptop is hot enough as it is. It's not up there in that kind of heat density. So the problem was, how do you get the heat out of that kind of a processor? And what does this come from? It's because the dynamic power, the amount of power that is being consumed because of the actual switching and stuff that's going on in the processor, is proportional to the voltage squared times the frequency times the capacitance. And so if we increase the clock rate, the frequency, we actually get a cubic effect, because if we increase the number of cores, we're actually only going to, it increases the capacitance, but only linearly. So we have to, what happens when we tried to make the clock speeds faster is they were getting hotter and hotter. And there's other laws that for a while this was kind of okay, Dennard scaling, but at this point now, in about 2004, 2005, the processor designers really hit a wall in terms of making processors faster. So what did they do? They did the easiest thing, or the only thing they could think of kind of in quickly, which is I've got to design for a processor. Moore's law is still continuing, so I can put a lot more transistors on my chip. What will I do with that? I'll just plop down multiple copies of my processor. And then, as I said, the marketing people came involved and said, you can't call those things processors because then people will know that the processors didn't get any faster. We'll call them cores, and we'll call the whole set of them a processor and say it's 4 times faster because you put 4 copies of it on the chip. Okay. Marketing is also important. Oh, what happened to my, let's see. So this was the transistor density curve now extended out to 2010, and so that's still transistor density in thousands. There's the clock speed frequency. So it may not be obvious, but this is actual real data, measured data, and you can see that it leveled off in about 2005. What happened instead is the number of cores, which used to just be 1, right, so we didn't plot it here, now became greater than 1. And that was going up to make up for the fact that we had these transistors, but we couldn't use them for faster clocks. And the power, by the way, was also going up, and you can see it hasn't completely leveled off, but it did level off somewhat. And the real problem was not just how do you power the processor, it really was how do you cool it, right? How do you get heat out of that thing? And so that was one of the reasons they went to these multi-core designs. So dual core, quad core, et cetera, is what we were seeing, and now we're seeing many more cores as you extend this out into 2017, 2018, especially when you get to supercomputers where people actually know what to do with all that parallelism. It turns out that there's some feeling that the processors that are kind of in this time frame, and let's say the 2005, that time frame, were over-engineered. They were working so hard to try to get try to keep from making people write parallel software. They were putting all this hidden stuff into the microarchitecture, such as parallelism that you didn't see. All that parallelism also was consuming power, and so they were kind of over-engineered for the serial case. Once you said, oh, forget it, we're going to have to go parallel, you can actually slow them down, and you can, and that's why you see some of the clock speeds actually come down in things like the supercomputers and in other kinds of devices. Okay, so this is why parallelism is here, and why even if you're not interested in supercomputing, in this class you're going to be learning about multi-core programming and GPU programming and other things that are important on a single node, although we will also try to get everybody to look, and will in the homework assignments look at large-scale parallelism as well, so you can see what that looks like. Okay, so what about Moore's law? Well, it turns out that Moore's law is in trouble as well. So even though we've been still riding this Moore's law curve, putting more and more transistors, we're having trouble with it, and there's a couple of reasons for it. But this slide that I got from one of the EUV project up at the lab really, and it's, let's see, where is it from? It's from this EUV symposium, is looking at the complexity of designing computer chips. So what's the problem? So probably one of the first technology problems you run into is lithography. That is, the way you make the chips is you make this mask, and then you have to shine light on it, and you have to make a chip from that mask. So when the feature size gets very small, now you can imagine you've got this cutout, this stencil, and you can get all these errors because the lines kind of run together and things like that. So one of the things they do is they make the masks, they use multiple masks in order to get the little tiny features they want. So it's like, I don't know, one of those games where you kind of put down one mask and that you get certain lines that go this way, and then you put down another mask and you get the lines that go this way, or whatever, different features from different masks. So at 7 nanometer, which is kind of what they're currently trying to get to, you have 33 masks. So you might say, well, okay, so who cares? Well, each of those masks takes time for them in the fabrication process. So as the number of masks increases, first of all, your yield rate has problems because you're getting more errors because you've got little tiny features. And secondly, it's very expensive because making a chip is no longer you just got one mask and you use that mask and then you're done with that whole chip. You've got these 33 steps, and each one of those is quite expensive. So there's an alternative technology, which I won't really talk about here, EUV lithography, but I think the more important thing for this class is just to understand that it's getting harder and harder to make chips with smaller transistors. That is also related to the fact that the cost of having a fabrication facility, this is looking at something called Moore's second law or Rock's law, which is the cost doubles every 4 years of building a kind of state-of-the-art semiconductor facility. And that's in millions of dollars. And over here we're looking at these die costs dropping, but also chip costs not dropping quite so fast. So if you can't use the chips that you're fabricating because so many of them have errors because the feature sizes are so small that there's just a couple of atoms in the wrong place and it doesn't really work anymore, you have to throw them out. And so that also produces a lot of problems in the yield. In fact, where was that picture? I thought I had one more. So let's see, the processor that's on the Cori system, the Knights Landing processor, as fabricated, that actually has 76 cores on it, but they're only using 68 of them. And the reason is because then if the chip is bad, as long as you've got 68 good cores left, you can still sell it as a Knights Landing processor. So they put extra chips on there. And that is also another reason behind parallelism, which is if you've got a smaller number of simpler cores, you can as long as you've got sort of a certain number of them that are good, you can still sell the chip. Whereas if you only had, say, 4 big, huge cores and one of them is bad, it's much harder to sell a 3-core chip. But selling a 68-core chip that has a little bit of wasted real estate on it is still possible. Okay, so in 2018, we've got all of these processor vendors are really producing multi-core chips. So this is no longer, there used to be sort of a theory, the sky is falling, parallelism is going to be important. Nobody believed us, nobody believed the hardware designers who said that, and now it's absolutely true that parallelism is everywhere. The big question has been what commercial applications that will drive the industry. So what kinds of applications, which by the way tend to not be science applications, but what applications that people will pay a lot of money for can take advantage of parallelism, which is why there's, by the way, so much interest in things like machine learning as a driver for those computer architectures, and we're seeing specialized architectures for that as well. All the programmers have to be parallel programmers, and there was a big bet on parallel computing, and it is basically here to stay. And as I said, in this machine learning arena, you can look at things like GPUs, which were originally designed, for the entertainment industry, for games and so on. And now it's really being something that is recognized as being really valuable for doing deep learning, in particular convolutional neural nets. That is also having an effect on the industry and putting more interest in these different kinds of parallel architectures, not just multi-core processors such as the kind that are in your laptop, but also processors that are these graphics processing units that have even more parallelism on them. So Moore's law reinterpreted, the number of cores per chip doubles every 2 years instead of the speed of the processors. Clock speed doesn't increase, and it might even decrease, and it has decreased in some cases. And we need to deal with millions of concurrent threads. Actually, for exascale, people are talking about even billions of concurrent threads. And you have to deal with parallelism that's on the chip as well as parallelism between the chips. But even with all of this parallelism stuff, Moore's law is not forever. But basically, the things that are looking at Moore's law are also going to lead to address Moore's law are also going to lead to more kinds of parallelism, because in order to deal with the power issues, you're still going to look at putting lighter weight processors, having switches and things like that switch more slowly. That may not have to do with the size of the device, but has to do with the amount of power that it uses. Okay, so that's a little bit about why parallelism, why it's kind of ubiquitous now throughout parallel computing. Any questions? Okay, So the last thing we'll do, and then I'll talk a little bit about the rest of the course, is talk about measuring performance. And I actually added these slides this year because I found that even when we got to the end of the semester and people were doing final projects, there were sort of some basic things about reporting performance numbers that I think not everybody appreciated. And so I just thought we would talk about performance and what are some of the pitfalls that you can run into. There's a great report called 12 Ways to Fool the Masses by David Bailey. So this takes some inspiration from him, but I'll also give you kind of my own perspective on this. So this is the most common performance kind of graph that I see in like an early CS267 project. It's running time, which is great because this is actual running time, which is what people really care about. The problem is, I don't know, what can I tell from this? It looks good. It looks like things got faster, but so much of the information is down here, I really can't tell how things are going. Now, of course, I can put this on a log scale, and that's a little bit better because I've got a log scale down here in terms of the cores. This is up to, you probably won't be running problems this large because you won't have a big enough allocation on Cori, but Cori would give you enough processors to do that, but you'll maybe be somewhere over about here. But still, it's a little bit hard to know what to make of this kind of running time plot unless you're really good at reading maybe log scales and trying to infer exactly how far you are from optimal. So a typical thing to do is report speed up, and that's a really common thing to do in any kind of parallelism paper. If the point of the paper is, or the study that you're doing is to say how much value do I get from parallelism, then we look at speed up. That is the time running on one processor divided by the time running on P processors. So, and this is what we call a strong scaling plot. That is, we've got one problem, and we only care about solving that one problem, and we're going to try different numbers of processors and see how fast we can make it go. And now we can see, and this is, by the way, exactly the same data as in the previous two plots, but now plotted as a speed up curve. Now we can see that it leveled off, right? We didn't get perfect speed up. It makes it more obvious if we do something that's very helpful for the instructors in the course. You put a linear speed up line in there. So what would this speed up look like if it were perfect? Well, that's the red line. And now we can see that my actual code is running at something that's clearly not linear when it gets out there far enough. Now, up to what here, maybe 128 or so, we're doing great. Maybe even up to 1024, you would say, you're still doing pretty well. Okay, so what's going on? So this is synthetic data. It's just all a little Excel spreadsheet with some formulas in it to plot these things. Once again, this is a strong scaling plot, so I'm just thinking of this as I've got one problem I'm trying to solve, and what is the kind of most obvious reason, or what's in this performance data that's causing it to not give us a linear speed up? And then we'll see many things that will cause us to not get linear speed up, but the most obvious one here is Amdahl's law. Okay, so Amdahl's law is this gap in between perfect scaling and the linear speed up. So what does Amdahl's law tell us? It says that, let's say that we've got some application and only a piece of it is parallel, and some piece of it, and hopefully a pretty small piece of it, is serial. So S is the fraction of work that has to be done serially. P is the number of processors we want to run at. We calculate our speed up, which is time on one processor divided by time on P processors. This is going to be 1 over, so I'm just kind of normalizing it here, so S plus 1 minus S times P. So the part that parallelizes we're going to assume that gets perfect linear scaling for the 1 minus S piece of it, but this is going to be less than 1 over S. So it doesn't matter what you do in your fancy parallel algorithms. If you've got some fraction S of your application that has to run serially, you're going to run into this Amdahl's law problem. And so, in fact, I think S on that previous graph was it 0.001, so 0.1% of the running time. And so that 0.1% is not a problem until you get up to 60,000 processors, and then it becomes a real bottleneck. And you might think that, well, this is of course obvious to everybody, but I will tell you, in this biology project we were working on, we had a little serial bottleneck in the code, and the first few data sets we ran it on said, no problem, we're never going to see this serial bottleneck in practice because it's such a small fraction of the running time, it doesn't matter. Then we took a big environmental data set and put it in there and tried to run it on a large number of processors, and guess what? Amdahl's law hit us, and it looked exactly like that curve that I just showed you. So, so you really do have to worry about Amdahl's law. And so, Cori has about 650,000 processors. The fastest machine, Taihu Lite, has about 10 million processors. So Amdahl's law, if you're trying to run a computation across an entire machine, is you've got to have really tiny Amdahl's law fractions if you're going to worry about parallelism. Things like I/O and all that kind of stuff often end up being your, can be your Amdahl's fraction. So another way to look at data is often to look at parallel efficiency. This is exactly the same data I showed before, but as an efficiency graph. So this is just saying, assume that my performance at one processor is 100%, and now as I look at parallel scaling, how does it drop from 100%? So I'm just looking at those, just another way of looking at the speed up numbers. This is also a strong scaling plot, and also looks obviously bad as you get to a very large number of processors. Also may be fine if you're only up to 32 or maybe even up to 128. So the biggest problem with speed up numbers, and one that David Bailey kind of hammers on about all the problems with speed up numbers, is you don't want to only report speed up numbers. Because what is the basic problem with speed up numbers is, what is your serial baseline? What is that the time at one? What did that come from? And so there's many ways in which this can go wrong. One is use a 64-bit baseline and then run the parallel version in 32 bits. You see this kind of stuff sometimes in GPU comparisons, because I'll run in 32-bit mode. Use a bad algorithm for the baseline because somebody else gave you the code or whatever. Or compare it to something that's in another publication. Use a bad implementation for the baseline. So a lot of times what you will find is as you're trying to make your parallel computation go faster, you'll figure out things that would have made the serial computation go faster. You need to go back and put those optimizations into the serial code as well. The opposite problem in some sense is, I built some new programming language, and it's really cool, and it has this really great and very sophisticated runtime system, and I'm going to use that on one processor as well as all of the other processors. So now it kind of seems fair, right? Because I'm using the same runtime system for all the processors. But that parallel runtime system can be really, really slow, and so that single processor time is really bad, and so it's not really fair to compare it to that. So you usually try to use the best possible time you can get for one processor, whether that's your own implementation or somebody else's implementation. And you also, whatever you do, need to report what that serial baseline is. That sometimes people switch processors, and if you don't report the running times at all, if you only report speed up, that can be really confusing. So the main point is that you often want to report speed ups or efficiency because they are, it helps you understand the value of parallelism, but you also want to make sure you're reporting absolute running time. Another really common way to report numbers, and this is especially common if you're going to run up here at, say, 65,000 cores, 64,000 cores, is to look at what's called a weak scaling problem. So in weak scaling, what I do is I say, let me take a certain size problem, and I'll run that certain size problem on one processor. I'll take 2 copies of that, or a problem that's twice as big, and run it on 2 processors, a problem that's 4 times larger and run it on 4 processors, and so on. Now you need to be a little bit careful when you do this, but you can compute something like efficiency then, and you'll see these plots. Oftentimes they don't start at 1, they might start somewhere over here in the middle, but you can at least then get a problem size, because typically the problem you have is a problem that's large enough to run over here on 64K cores will not even fit on a single core, a single processor. So you can't run a strong scaling example on a big, huge machine. But weak scaling, I can take a problem size and scale it up and down. What you want to do is look at something like floating point operations or some other rate per processor, and you're looking at the rate per processor as you change the number of processors, and that should remain constant if you have perfect efficiency. Whereas here we've got some drop off, but at least it looks good. Now why do people care about this? I mean, sometimes people will complain about using weak versus strong scaling, but there are many problems in which you have a bigger computation you want to run, you have a bigger data set. So in the genomics case, that we can't possibly fit onto a single processor, or you have a big simulation that you can't possibly fit. It would take you so long to run it that it's not even worth trying to run it on a single processor, or the data simply doesn't fit. Okay, so that's a little bit of kind of a few lessons for today in terms of what you should learn from the course. What else is going to be in the course? Well, we're going to teach you about parallel programming models, and there's really three overarching kind of ideas in parallel programming. There's what we call shared memory programming, distributed memory programming, and data parallel programming. And these are the specific languages or libraries that you're going to use for each of these, and they kind of overlap. So shared memory, the kind of canonical example used is OpenMP. If you've programmed in P threads, you also seen a similar kind of shared memory programming model. You'll see one in homework 3 called PGAS. That is kind of like shared memory, except that you can run it in a scalable way in distributed memory. MPI is kind of the canonical distributed memory example. Spark and CUDA, very different programming models or programming environments, but they both kind of give you this idea of data parallelism, which, by the way, also comes up in MPI in their collectives. So we'll try to give you a kind of overview of these different techniques for programming them. The second main concept we want you to get out of this class is the idea that there's really a fairly small number of parallelism strategies that you can use. And we do this by surveying some of the main methods that come up in science and telling you how to parallelize those. So even if you go out and work on a completely different problem, let's say machine learning, and you say, oh wait, but this is a sparse iterative solver. I saw this in CS267, and the way they parallelized it looks like this, and now you can apply that to other things. So there's kind of high-level patterns that will come up, and you'll see those in parallelism. We want you to see some performance models, the roofline model I mentioned, a couple of others that will come up, and cross-cutting themes, communication avoiding algorithms. I already told you about Amdahl's law. There's a few other laws you'll see. So I just want to put this up here, the course mechanics as we're wrapping up. Be sure that you look at homework 0. It's due a week from tomorrow. It is just to write a kind of a simple write-up of some parallel computing problem that you would be interested in. It is not committing you to a particular final project, but we will make them public, and it might help people in the class find other people who have an interesting problem to work on. It can be your own problem or something from somebody else's group, something you find on the internet, and there's examples of it online. Secondly, fill out the survey, which you should get access to through Piazza, and sign up for a NERSC account. So those are the main things that you want to do. Here's a little bit about grading. If you care about the details, 50% of it is the final project. The rest is spread out through the homeworks. So any questions? No questions even on the course mechanics. Okay. Well, I think I'll end there since our time is up, but you do have, you've got the information. The slides are online. If you have trouble finding the course website, go to my website or Jim's website or Aiden's website. They're all linked. Thanks very much.